senior research scientist at CaJAGWR and a senior faculty associate here at Caltech, and he'll tell us about cosmology and the future of gravitational waves.
Thank you very much. So in this talk, I'm going to argue that a space-based gravity wave mission that's very sensitive in the decihertz frequency range would be able to do very high precision cosmology. That is to say, would be able to measure cosmological parameters like the Hubble constant, omega lambda, omega matter, W, WA, much better than any other proposed mission and with much far better systematics. This is true despite the fact that BBO and Decigo, which are the currently proposed decihertz missions, weren't designed with that in mind. The main design goal for BBO and Decigo, Big Bang Observer and Decigo, is to measure a stochastic gravity wave background from inflation. So here's a schematic of either BBO or Decigo. At this level, they look the same. What they look like is 12 satellites arranged in 4 constellations of what I like to think of as mini Lisas, 4 groups of 3. So we have 2 overlapping groups of 3 here, forming a Star of David. And the point of that is that you basically have 2 detectors here, and then can cross-correlate their outputs to get the stochastic gravity wave background, much as one cross-correlates Livingston and Hanford to get the stochastic gravity wave background. So that's the point of these 2 constellations. What about these 2? Well, the point of those is that probably 2 orders of magnitude above the stochastic gravity wave background you're looking for is a huge foreground from all the coalescing compact binaries in the universe, about 300,000 neutron star, neutron star, neutron star, black hole, and black hole binaries. To get down to the stochastic background, you have to basically subtract out all of them. And the point of these 2 extra constellations is to help detect and identify and subtract those out. Okay? The main point of this talk is that catalog of foreground noise sources is actually a gold mine for doing cosmology. For each one of those foreground sources, BBO or Decigo will be able to get the distance very accurately. And also, the angular resolution of these missions is so good that in most cases you'll be able to say uniquely identify the host galaxy. Say it's that one. And then go back and get the redshift. So you'd be able to get about 300,000 points on the distance redshift curve, and then it shouldn't be too surprising from that you can do cosmology extremely well. So Dan Holtz and Scott Hughes have referred to sort of binaries for which you can get both can get a redshift as well as a distance as gold-plated binaries. And in the field, we've always thought of like getting a handful of them with LISA or something like that. But yeah, I claim that a mission like this gives you 300,000, hence the title, Cosmology with 300,000 standard Sirens. It's not working. Right. Okay. So the context of this is, so it's been known for a long time that coalescing binaries could be used as sort of standard candles or standard Sirens for doing cosmology. But let me just review some of the history of that subject to put this in an intellectual context. So as far as I know, it was Bernard Schutz who first pointed out that if you have a network of gravitational wave detectors that detects some coalescing compact binary, then you can get the distance very accurately. Why? Because the distance is just equal to 1 over the amplitude times factors related to the masses and the orientation of the binary, which you also get from the waveform. And importantly, that distance is just based on incredibly fundamental physics. So just understanding the two-body problem. So it's much cleaner than any other distance measurements in astronomy. There's no distance ladder to go through. There's no worry about evolutionary effects. A binary is a binary is a binary. The problem is that because Einstein's equations are scale invariant, the gravitational wave signal tells you nothing about the redshift of the source. So where in gravitational wave astronomy we have sort of the opposite problem of optical astronomy. In optical astronomy, redshifts are easy, but distances are quite hard. In gravitational wave astronomy, distances are relatively easy, and redshifts are impossible unless you get some extra information somehow. So how might you get extra information? Well, there could be some, usually the thinking is there might be some sort of burst. So if two neutron stars collide, or a neutron star and a black hole, there could be a gamma ray burst. That allows you to find out where it is, and you then go get a redshift. Or if two massive black holes merge, there could be some disk dynamics that generates X-ray luminosity, and again allows you to localize the source and go back and get a redshift optically. Holtz and Hughes wrote a paper a few years ago considering what happens if LISA measures a handful of these gold-plated binaries, that is to say, binaries, coalescing black hole binaries for which you can get a redshift. And they showed that if you could forget weak lensing, which affects the distance measurement, if you could forget weak lensing, then you could probably measure the Hubble constant to about 1%. Currently it's known to about 5%. But unfortunately, weak lensing is an extra large noise source. And including weak lensing, you wouldn't get any better constraints probably than you have already, though they at least would be so independent of the current measurements. Satya Prakash, Schutz, and Vandenbroek wrote a paper just a few days after we submitted ours, or submitted theirs just a few days after we submitted ours, asking what the Einstein telescope, a third-generation LIGO-like instrument, could do if it also had, based on gamma ray bursts. So, so gamma ray bursts are often thought to come from mergers of neutron stars. Assuming that 1,000 of those were seen, they asked how accurately could the Einstein telescope measure cosmological parameters, and the answer was modestly well, sort of omega lambda to 4%, omega matter and W to about 18%. And that's actually, somewhat worse than current constraints, but also at least it's an independent method. Again, I'm just trying to put these things in context. And the last idea I'll mention, because I think it's kind of cute, is Macleod&Hogan pointed out that you actually don't necessarily need to uniquely identify the host galaxy to get interesting information out. Because galaxies are clustered, there's extra information from that. So for instance, if LISA detects an emery, that is to say, say a black hole, small black hole spiraling into a large one, and there are tens of thousands of galaxies in its error box. Nevertheless, in that error box, there are just a finite number of clusters of galaxies. And so you could imagine assigning it to each one of each. So for each cluster you imagine assigning to, that cluster basically gets a vote on the Hubble constant, right? And so, for instance, for one emery, you'd say, well, this cluster says the Hubble constant is this, another cluster says it's this, et cetera, et cetera. If you compile together about 20 emeries, well, so for the misidentifications, the votes will be random, but for the correctly identified one, we'll all vote for the same Hubble constant. And they conclude that with about 20 emery events at z less than 0.5, one can measure the Hubble constant to about 1%. So that's an interesting idea. Back to BBO. So here's the BBO noise curve. It's it's moved over, compared to the LISA noise curve, it's moved over about 2 orders of magnitude higher in frequency. And it's down almost 3 orders of magnitude in sensitivity. So it's a much more ambitious mission. Let's compare it. So here's the noise strain from a gravitational background of omega is 10 to the minus 15. Notice that's well below the noise curve. That's why you need to cross-correlate 2 interferometers, those 2 in the Star of David, to dig down to get it. But notice also that there's this foreground from all neutron star binaries in the universe, which is sitting above the BBO noise curve. and so obviously above the background. At first, so that at first is almost indistinguishable from the stochastic background. So you have to subtract out basically every single one of these neutron star binaries before you could get down to here. So the instruments are designed, BBO and Decigo, to be sensitive enough that you could basically remove all of these neutron star binaries and black hole binaries. I should say that in this paper Dan and I wrote, and in the rest of this talk, I'm going to use the BBO noise curve as my benchmark. That really was just for simplicity. I am also a big fan of Decigo. It was just a choice. But I think that most of the things I say in this talk will apply it will be as interesting for Decigo people as for BBO people. It's not easy to get down to that BBO noise curve. I mean, it's really, it's a LISA on steroids, basically. Smaller, but much more powerful. So it's non-trivial. We're talking about laser powers of 300 watts, 3-meter mirrors, arm lengths 100 times smaller. That's to get the frequency higher. Talking about doing it slightly in the ultraviolet. Acceleration noise 100 times better than LISA. So it's a major jump. At a higher frequency, so it's not that's true.
More or less an extrapolation.
I think it is. That's right. I don't think the acceleration noise, I don't think, is the big challenge. I said there are about 300,000 neutron star binaries you'll have to subtract out. Here's a plot of their distribution, their cumulative distribution in redshift. This is based on sort of a plain vanilla estimate of the neutron star merger rate and then an extrapolation to higher Z by Belchinski et al. So, you know, most of them are between Z of about 1 and 3, right? I think about 15% are Z less than 1. So they really have a lot of them in this very interesting redshift range of 1 to 2, where you get a lot of where you learn a lot about the cosmological constant, etc. So you're looking through a pretty large range of Z. I should just mention that you might ask, is it even possible to subtract out all these 300,000 neutron star binaries? And here I'll just make a one-slide summary of a talk of work I did several years ago with Caltech&Hams, which showed that we think it is. We sketched an algorithm for how you would do it. I'll just tell you roughly how the algorithm goes. It's very simple. You can imagine someone gives you this data set with the BBO noise and all the neutron stars in it. First, take out the brightest neutron stars, which are roughly the closest ones. Well, that brings down the noise curve a little bit. So you can push out a little bit farther and get out and look out for neutron stars a little bit farther than that, which brings down the noise curve a little bit after you subtracted them out, and keep going like that. And we showed that for the baseline BBO sensitivity, that the noise curve goes down fast enough as you push out that you can just keep pushing out as far as they go, at least beyond to Z equals 5 and beyond. So that would be true for the BBO noise curve, but if it were actually worse by a factor of 3, it would cease to be true. So the BBO noise curve is not, so at least for this algorithm, you have to get pretty close to the BBO sensitivity for it to work. Yes, Maurice?
Could you have a numerical roundover ever
That's a very good question, and we also answer that in the paper. I just didn't mention it here. And we showed that the subtraction, that's a very good question. What Maurice asked basically is every time you take a binary out, you actually leave a little bit of error in, right? Because you don't ever take it out perfectly. And the whole signal is much bigger than the background, so you might worry that the sort of sum of all the residuals will drown it. And we show in the paper it's not true. Okay? It's a reasonable worry, but you can get away. Or a better way of saying it is that we have an algorithm also for dealing with that residual error that basically projects it out. So that was a good question. you should understand for this talk that the time scale on which, say, a neutron star goes through the BBO noise band is of the order of years. For example, to go from, say, 0.2 hertz all the way to the end to merger is about 1 year for 2 neutron stars at low Z. To go from 0.1 to 0.2 hertz is 4 years. Okay? So it's order of years. For black holes, it's more like weeks. So that's the time scale. I'm going to show you results of calculations that show you BBO's distance, determination accuracy, and angular resolution. I'm just going to quickly summarize how that works, what goes into those calculations. I basically follow the standard recipe that many of the people in this room have heard a million times. So I use the Fisher matrix formalism. Right? BBO essentially produces 8 time series. So remember, it's like 4 Lisa constellation, and each Lisa is like 2 Michelson interferometers because it's a triangle. So basically you get 8 gravity wave signals. For this calculation, we're neglecting spin precession effects. The objects are pretty far away. Spin precession is not so big important anyway. So then there are about 10 parameters but we do include spin-spin and spin-orbit interactions in the phase. So that leaves 10 parameters on which the signal depends. Then we calculate the Fisher matrix, gamma mu nu, just by the inner product of dh d lambda mu, dh d lambda nu, where mu and nu run from 1 to 10. And we use this inner product as a standard noise-weighted inner product. And then the covariance matrix of the errors is just the inverse of the Fisher matrix. So if you haven't seen this before, you didn't understand a word I said. But if you've seen it before, it reminded you. So that what goes in. Here's what comes out. First, for BBO's angular resolution. And first, what would you expect? Well, the idea is that BBO's angular resolution really comes mostly from time of flight. You've got these 4 constellations in 3 different parts of the solar system, and a gravity wave from there hits this constellation first, and this constellation second, and this constellation third, and from the time of flight differences, you can figure out where it was on the sky. So based on that picture, you can say, what's a rough estimate? Well, it should be 1, it should go like 1 over the signal to noise, and basically 1 over the number of wavelengths, gravity wave wavelengths, across the solar system. And that's about an arc second, okay, for neutron star binaries at z equals 1. So that's a crude estimate. And then the Fisher matrix calculation, you get about the same thing, roughly. So these are curves for black hole, black hole, black hole, neutron star, neutron, actually the other way around, neutron star, black hole, black hole, black hole, neutron star binaries. Angular resolution arc seconds squared, ranges between from 0.1 to 100 or so arc seconds squared, depending on the components and the redshift. So much better than any other gravity wave instrument, obviously. And for the BBO's distance error, well, typical signal to noises are of the order of 100 or so, or several hundred. So you would expect distance resolutions of the order of 1 over that, or something like 1%, and that's also true. It comes out of the calculations. So again, black hole, black hole, black hole, neutron star, neutron star, neutron star, and you get answers that vary from from down to 0.1% to a couple of percent, 2 or 3%. So excellent distance measurements. What I just presented were the distance measurement errors due to noise in the detectors. Actually, in reality, the distance measurements distance errors will be dominated by weak lensing effects. Just as density and homogeneity in the universe cause galaxies to be a little bit brighter or a little less bright than they would be otherwise, they affect the amplitude, the measured amplitude of the gravity waves. And the effect is actually larger in this case than the errors due to noise. So the typical error, the relative distance error is like 4% times z. Okay? So in almost all cases, it dominates the error. Where weak lensing dominated in terms of distance errors. I said at the beginning of the talk that that the BBO's angular resolution is good enough to uniquely identify the host galaxy. It's this curve that typically, not always, that demonstrates that. So for black hole, black hole, black hole, neutron star, neutron star, neutron star binaries, as a function of z, I plot out here now what's the occupation number of a typical error cylinder. That is, an error cylinder is a little sort of like circle on the sky or ellipse on the sky times some distance uncertainty in z, where the uncertainty on the sky was given by the noise and the uncertainty in z is dominated by the weak lensing. And you can see it's always less than 0.3 something, and usually much less. So even for the very worst it gets is 0.3 something at z equals 1.6 or 7 for neutron stars. So even for neutron stars, mostly you'll get the right galaxy, 80% of the time. And for black hole, you'll almost never miss them, right? You get them, there's only one in there. Okay. Now, so I've told you that usually you can uniquely identify the host galaxy and get the distance quite accurately, limited by weak lensing. Now, and you can do that for hundreds of thousands of sources. So how well can you determine the cosmological parameters from that? So again, I'm just going to tell you what goes in and then what comes out. So what goes in is, this is with Dan Holtz and I, we assumed we have, say, 250,000 neutron star binaries out to z equals 3. This was just to simplify it slightly. And we assumed that someone had perfectly given us the redshifts. Okay, they'd gone out and and there was no errors from those. And then we fit those results to models with cosmological models with 5 parameters. The Hubble constant, omega matter, omega lambda, I should have been a lambda there, sorry, W0 and WA, where W of z is p over rho, and WA is basically its first derivative. So that W0 is its value today, W is this p over rho, W0 is its value today, and WA is basically dW d log A. Okay, it's telling you how fast W is changing. Okay, and following the standard convention in this field, we also assume a forecasted Planck prior. That is to say, we'll assume that by the time BBO flies, we'll know from Planck omega matter times h squared to about 1%, and plus there's also an additional constraint on basically the Hubble scale at decoupling from the first peak. Okay, and this is the way this is what one usually does in this field. When one's judging dark energy emissions, you assume you're going to learn something also from CMB. And here's what comes out, again, from 250,000 neutron stars up to z equals 3, you'll be able, if you just project the uncertainties into an omega matter Hubble constant plane, you get, these are the 1 sigma and these are the 2 sigma errors. So you'll be able to measure Hubble constant to 1%, 0.1%. It's currently known to 5%. That's 50 times bigger. And that was for the full 5-parameter model. If you take, okay, let's say I know 2 of those parameters. Let's say it's a lambda CDM model. So I know that W0 is 1 and WA is 0. Then you can measure the Hubble constant to a 40th of a percent. Okay? Again, that's because we have 300,000 sources. How well can you do on the other parameters? These dark energy parameters, W0 and WA. Well, you can measure W0 to 0.01 and WA to about 0.1. There's a standard dark energy figure of merit, which is basically the area of this ellipse. So you judge dark energy emissions by how small an ellipse you get in this plane. And this ellipse, in this figure of merit, is about 10 times better than you get for all other dark energy emissions combined. Yes? This is including the weak lensing, yes. It would be much better without weak lensing. It's weak lensing limited. Okay. So I hope I've convinced you it would be a pretty amazing cosmology mission, BBO, or Decigo. Now I'm going to tell you it's actually also a great weak lensing mission. So I'm changing the subject. It's a great weak lensing mission. Why is that? So imagine you've taken all these 300,000 binaries, and you've measured the luminosity distance, that's here measured on this axis, versus the redshift, okay? And for each one, you get a little black point, okay? And then you find the best fit, which is the cosmology, which is this red curve, and then blown up over here. Well, you can ask yourself, what's keeping all those black points from lying on the red curve? And again, the dominant reason they don't lie on the red curve is weak lensing. There's a small error due to noise, but there's a bigger error due to weak lensing. So the distance of every single point away from the red curve is a measurement of how much that binary was lensed. And you get 300,000 weak lensing measurements, each with significant signal to noise. Notice this is different than the way weak lensing is usually measured. The way it's usually measured is weak lensing produces shears in galaxies. Galaxies look elliptical anyway, so you have to, over a large field of galaxies, you look for some net correlation in the shears of the shapes of the galaxies. Here we're not measuring shear, we're actually measuring convergence, the amplification. Okay? Well, how good a weak lensing mission is it? So I'll give you just two measures of that. One's a very kind of crude measure. You could say, what's the total signal to noise squared you get from measuring weak lensing in this whole ensemble of galaxies, of binaries? And basically, the rho squared is just the sum over all measured binaries of the magnification over the error in the magnification. So this is the magnification due to weak lensing, that's most of it, and the error is due to noise. And if you add them all up, that's about 10 million. Okay? And if you look at the most optimistic versions of all other weak lensing experiments, like the most optimistic versions of JDEM or LSST, that's about what you get. So it would be comparable in power to the strongest other weak lensing missions. And by the way, I think it's interesting that if you ask where does this 10 to the 7 come from, so about half of it comes from neutron star binaries, and about half of it comes from black hole binaries, at least for our fiducial estimates. How is that possible? Well, we were assuming that the black hole merger rate is about a 20th of the neutron star merger rate. That's a typical assumption. So there are 20 times fewer in the sum. On the other hand, the magnification, on the other hand, the error, delta mu, is about a factor of 5 less, because the signal is stronger. So you gain back a factor of 25. So in fact, they're about comparable, which makes it, I think, a more robust estimate. You can ask how well BBO, so you can also, the typical thing you do with weak lensing is measure the power spectrum of the weak lensing, basically from the 2-point function. And it's interesting, the convergence power spectrum is exactly the same as the shear power spectrum. So we're trying to measure the same thing as everybody else. And this is how accurately you can measure it. And I just claim if you compare it to other proposed missions, this is very, very good. So you could constrain it to within these two red lines. And really, we've just begun this weak lensing analysis. So that's as far as we've gone. That was just a first cut of how well we think we could do. There are a lot more things you could do with this. For instance, we haven't yet asked how well you could constrain cosmological parameters like sigma 8 with these measurements, but we plan to do that. Or I think even more interesting, maybe, is to look, so imagine you did both kinds of weak lensing measurements. You got the shear over the whole sky and the convergence over the whole sky. So you get a basically a map of the whole sky of both. If you put those two together, is there some extra? Is you just kind of double the information, and which is not so great, or are there sort of extra synergies and does it break degeneracies if you've got both? I haven't thought about it. It's a question I'd like to think about. I've mentioned that, of course, that and BBO can't do the whole job itself, you need to rely on optical astronomers to follow up your observations and give you the redshifts. So how realistic is it that someone's going to be able to come back and give you 300,000 redshifts? So I'm not an expert in this, but I'm going to argue that it doesn't sound so ridiculous, especially on the time scale on which BBO will fly. So by the time BBO will fly, the LSST, which I'm presuming will have been built by then, will have already given you photometric redshifts for about a third of all galaxies on the sky, to about 2 or 3%. Moreover, there are right now several proposed wide-field spectroscopic surveys like WIFMOS and Big Boss that plan to measure like 5 million spectroscopic redshifts per year over a third of the sky, whatever they can point up at, in the range 0.2 less than z less than 0.3. I'm just asking for 300,000. So it doesn't seem like a very unreasonable assumption that it will be one would be able to do this job. I'm not saying it's trivial, but it doesn't seem, compared to all the other things, I don't think it's a big deal. So I've told you that BBO would be a tremendous ultra-high precision cosmology mission, a very strong weak lensing mission. And, at this point I start to feel like I'm one of those guys in the commercials that says, oh, they're selling kitchen appliances. There's more. There's more. But there is more, because there's a lot of other science BBO could do. And I haven't even thought about it very much, but you immediately think of a number of examples. So one thing BBO could do is measure intermediate black holes at very high redshifts, the various earliest ones. So it's a standard picture that the earliest population 3 stars may have been much more massive than stars today, several hundred masses, could have left black holes of 100 masses, 200 masses, solar masses, 300 solar masses. And those might well be the seeds of the big black holes that we see today in the centers of galaxies, some of them. Okay? So if occasionally those two formed in binary, and presumably these were in dense systems, some of them, and then 3-body interactions would have made binaries, which then merged. At least BBO would see these to incredibly high signal to noise, all the way out to z equals 20. It could see beyond z equals 20, but I'm presuming that nothing happens before z equals 20. But it would see such intermediate mass black holes at z equals 20 with signal to noises in the 1,000, 2,000 range. Right? Based on simulations from Marta Voluntari, I've estimated the rate for these would be about 30 per year, of which about 20 per year are really at high z, at z greater than 10. You could say, will these be seen by anything else? So, for instance, the Einstein telescope would detect about, the 3rd generation LIGO would detect about 2 of them per year, but almost none of them at very high z. They'll all be at z less than 8. Just BBO is much more sensitive. So this gives you a direct look at the very first black holes at z equals 20. Tens per year. That's application 1. Application 1. The second is that BBO would be an advanced warning system for all gamma ray bursts, every single one of them. Short hard gamma ray bursts. So the standard assumption these days is that short hard gamma ray bursts come from mergers of neutron stars or neutron stars with black holes. BBO sees every single one of them and tells you exactly where they're going to happen months before they happen. In fact, BBO kind of over-predicts them because it tells you where every single merger is, and not all the mergers will presumably lead to observable gamma ray bursts because the gamma rays are beamed. But you'll be able to say for each one that, what the masses are, whether you did see a gamma ray burst or not, what the orientation was, be able to sort of correlate the gamma rays with the masses of the object, with the type of object, with the orientation on the sky, and investigate beaming. Presumably, for lots of those mergers, even though you don't see the gamma ray burst because it's not beamed directly after you, you would see the afterglow. So right now, people have searches for orphan afterglows. So you would presumably this would be, an early warning system for all afterglows. And so I'm just presuming that this would tell you a great deal about gamma ray burst physics. Another application is strong lensing of merging binaries. So this is very rough. So roughly about 1 out of 1,000 quasars is multiply imaged on the sky. And these binaries we're talking about are roughly the same kinds of redshifts. So as a very crude approximation, you'd expect roughly 1 out of 1,000 will be multiply imaged. Where for this, by multiply imaged, I mean you see the same binary twice, right? On the exact same parameters and the exact same point on the sky, but with a time delay of months to years, right? Unlike for most strong lensing measurements, well, the time resolution is just incredibly good. So one of the things you want to know is the time delay between the two images. I haven't calculated, but it's going to be much less than 0.1 second is the error. Okay, we measure it almost exactly over a year, and so you'll get about 300 of these, each of which gives you an independent estimate of the Hubble constant again. And presumably, though again something I'd like to look at, presumably all the time delays and all the amplifications of all the images probe the structure of the lensing galaxies and clusters, though I haven't really looked at that. That's just a presumed thing that's true. Okay. So I've told this spiel to some people before. I gave a talk on it before, and I've buttonholed some people in the hall. And I think it's fair to say there's sort of two kinds of reactions I get. One is, people are pretty interested. Wow, there's a lot of stuff, great stuff you can do. But I think even sort of a more typical reaction is when I say just the words BBO, people's eyes kind of glaze over in a way that I'm sure that when they're thinking of BBO, they don't see this. What they picture in BBO is this. You get it? Pie in the sky. So the question is it just pie in the sky, right? Is this at all a credible mission? So let me just talk about that for a bit. First of all, just as a sociological point, not everybody thinks this is pie in the sky. So in the US, there's really been very little attention to it in the last few years. But in Japan, there's actually a very big science community behind Decigo. There's a very big science team, and they've got a roadmap. And they have a three-stage program of Decigo Pathfinder, pre-Decigo, Decigo, with an ambitious launch date of like 2024. So they don't think it's crazy. Right now, the Japanese Space Agency is trying to decide between Decigo Pathfinder and one other mission for a launch slot in 2012. They say they'll decide this month. They said that last month, and they said it the month before. But presumably, before too many more months are over, they'll make a decision. And just so while I'm talking about Decigo, I should mention that even though that schematically they look very much the same, and the details of how they work would be rather different than with BBO. BBO is really a scaled-down LISA, scaled down in size. The idea behind Decigo is to build something more LIGO-like. So while BBO and LISA would use time delay interferometry, the idea in Decigo is to really use Fabry-Perot interferometers to shrink it much more, shrink it down to 1,000 kilometers, while BBO would be 50,000 kilometers, and have big enough mirrors that really all the light bounces back and forth. There's no in between those two mirrors. So we have Fabry-Perot interferometers in space. And then pushing on the satellites to make sure you're always on a dark fringe, and the same sort of things one does in LIGO. It's more LIGO-like design, or TAMA-like design. The other point, again, returning to the question of whether this is just all pie in the sky, is while the current versions of BBO and Decigo were based on the goal of measuring stochastic gravity wave background. So I claim that makes it very overqualified for this doing of cosmology. So to get the stochastic gravity wave background, you want to get every single neutron star and black hole in the universe, way at z equals 5 and beyond. But I think it's pretty clear that to do cosmology, if you get like a good fraction of them out to z equals 2, you're going to do almost as well. So something I'm looking at right now, my current project with this, is to see how much you could de-scope the missions and still get most of the cosmology out, even if you couldn't do the stochastic gravity wave background. And once you say that, once you say, well, maybe I'm going to sacrifice the stochastic background, then a lot of things are up for grabs, right? You can make the thing arm shorter, you can make the arms longer. There are a lot of things you can try to play with. For instance, you could say, well, if I'm not going to do the stochastic background, I'm going to get rid of the Star of David, and I'm going to maybe use the Einstein telescope on the Earth as the third vertex in the triangle. So Einstein telescope sort of overlaps BBO in frequency range. BBO is maximum, 0.3 hertz. Einstein telescope starts around 1 hertz or something like that. So you might hope that this sort of arrangement would have, angular resolution comparable to BBO. I'm working on that calculation right now. I'd hope to have a result for you, but it's not quite ready yet. But maybe something like that would work. I think quite possibly. And if that were true, I'm just showing you the way you can start thinking about this. You could imagine a possible plan, just to make it sound a little more plausible, where you maybe launch one mini LISA plus Einstein telescope, one of those constellations, that'll allow you to get all the rates for all these things. You'll get, for the gamma ray burst at least, you'll have good localization. You might even get good localization with this pair for some sources. And then you could start doing cosmology. You'd certainly see all the high Z and intermediate mass black holes. If that worked, well, you could put up another constellation and then do all of cosmology, all the things I talked about. And then if that worked, when it worked, you could then say, okay, that's great. We'll put up the Star of David and look for the stochastic background. It's just the ways of thinking about this. I should mention a caveat. And it has to do with calibration. So throughout this talk, I've assumed that the BBO is excellent calibration. That's true for LISA. So everyone in the LISA project thinks that the calibration will be accurate to something like 10 to the minus 5 or 10 to the minus 6, where the biggest error comes just from the fact that you don't know the exact frequency of the laser, say the center point of the laser frequency for the constellation. You know what it is on the ground, and then you put it in space, and then it gets heated or jiggled or something, and it could change by a little bit. So it could be in LISA, when you say you measure the distance, you say that's 2 gigaparsecs. So that's 2 gigaparsecs plus or minus 10 to the minus 6th of that. In LIGO, it's not like that. In LIGO, the calibration accuracy currently is like 8%. So you can ask, well, why is that? And the basic reason is that in LIGO, so in LISA, the test masses are really basically freely floating, or there are no forces along the laser direction. Okay? There are forces that keep you from bumping into the walls of the telescope, but no forces are applied on the test mass in the measured direction. In LIGO, of course, you always are pushing on the test masses to keep yourself on a dark fringe. And it turns out to be a hard problem to say exactly how hard you're pushing, whether you're doing it magnetically or doing it with photon drives. You could probably solve that problem with a lot of work, but at the moment it's not done that way. I'm sorry?
Before there were any lasers and before there was LIGO, on paper it was 0.2%.
Okay. Okay. That doesn't necessarily mean anything for Lisa. I mean, it's a sociological comment. It's a data point. Okay, that's fair. It's a useful warning. The reason this is important for BBO is that, well, I've assumed throughout this that sort of the BBO architecture from the concept study a few years after the concept study, there was a problem that was recognized in it. If you take the sort of BBO as designed in the concept study, and you ask how much power falls on the photodiode, because with these 300-watt lasers and these big mirrors, it's like 10 watts. And if you ask for the two, and these are slightly in the ultraviolet, if you ask, what can I buy today that doesn't saturate, it's 10 milliwatts, right? So it was realized afterwards that that we're oversaturating the photodiodes by a factor of 1,000. So the paper was written by Harry et al., in which they proposed then something like a little more like Decigo with a more LIGO-like design where you push on the test masses to make sure you're in a dark fringe and don't oversaturate the photodiode. Unless you're very careful about that, then you might end up with, LIGO-like calibration, and that's exactly what you don't want. Now, I've talked to the authors, and they just didn't even know it was an issue, really. So as a sort of an appeal to the instrumentalists out there would be to find a way of dealing with this calibration issue. I've talked to many instrumentalists, and I think I get general consensus that it's a solvable problem. I mean, one thing you could do is instead of having one photodiode, you just have 1,000 photodiodes. Another thing you could do is, just work harder on calibrating the force that you apply to the test mass by, for instance, having another cavity sitting behind the test mirror that reads out exactly how far it's moving in response to some force. So there's a design challenge here, but it doesn't sound like an unsolvable one. But that's an important caveat. And so as a summary, what I've hoped to convince you is that a very sensitive gravity wave mission in the decihertz regime would be an incredible ultra-precise cosmology mission, if you can solve this calibration issue. That these in-spiraling compact binaries, this foreground noise, is a real gold mine for cosmology, that you can get the parameters of the universe with very low systematics, with systematics that are unimaginably better, that are vastly better than anybody else's method, because the systems are so simple, relatively speaking. They can do all this other great science, like high Z intermediate mass black holes, weak lensing, gamma ray bursts, strong lensing. And really, the way I think about this, I sympathize with people whose eyes glaze over and think of it as pie in the sky. But again, because I think one can de-scope the mission and you still get a lot of the science out, the way I think of it is as, it's an existence proof that there's a mission out there that's really incredible in the decihertz regime, and that I'm hoping that I can convince some people to sort of that science is incredible enough that they're interested in thinking of ways to make it actually doable, and to make it, to bring down the cost, and to make it actually practical. So I'm hoping somebody in the audience gets interested. So thank you very much.